Welcome, IB students. We are continuing our study of topic 4. This is really topic 4.6. You probably have already watched the video on Venn diagrams and a tree diagram. Today we're going to look at a two-way table. So we have a classroom of 20 students. Each plays only one sport. The table below gives their sport and gender. Anytime I'm working with a two-way table, the first thing I do is I tally up each of my columns and each of my rows. So my first column, the number of students that play football is a total of 9. The number of students in total that play tennis is 5. The number of students in total that play hockey is 6. And that adds up to a total of 20, which matches my overall total. Let's add up our rows. So we have 5 females plus 3 plus 3, so we have 11 total females in the survey. And then for our males, we have 9 total in the survey. 11 plus 9 also adds up to 20. Okay, so we are ready to answer some questions here. So the first question says, calculate the probability that the student is a male or is a tennis player. So you could use a formula, or you can just grab your answers off of the table. I'm just going to start by grabbing the answers off of the table. So the probability that a person is a male, or that's a union, is a tennis player, is, and my total number of students is 20. And I'm going to circle the students that are male or play tennis. So the ones that are male would include the 4, the 2, and the 3. And the ones that play tennis would be 3 and 2. I don't want to double count that 2 though, so be careful there. And you're going to just total up all the number of people that I just circled. So that would be 4 plus 5 would be 9, 10, 11, 12. So we've got a total of 12 over 20. And you know IB allows you to keep it in an unreduced form. What if I wanted to show this exact same problem, but I wanted to use my formula? And the formula that I'm talking about is the combined events formula. This is in your formula packet under topic 4.6. And it is a formula that relates your union to your intersection. And so assuming that we don't know anything about whether the events are independent or otherwise, we can make connections between the union and the intersection, meaning that the probability that A or B happened would be the sum of probability of A plus probability of B minus the probability that they both happened. And so if you did not have this second part, that would actually mean that we have the probability of the A and B happening, and we would be double counting any overlap between the two. And we do have overlap on this problem. If you had a scenario where you know with absolute certainty that you don't have any overlap, that actually means the events are disjoint or mutually exclusive, which is your second formula down here, because the overlap would actually be 0. So you'd be subtracting a 0. But here I do have some overlap, so I'm going to use this formula, and I'm always going to start these problems by writing the formula down first. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B happening. And so I'm going to substitute in what I know. I am finding the probability that the person is male or plays tennis. So that would be the probability that they are male plus the probability that they play tennis minus the probability that they are male and they play tennis. So the probability that they are male, well, we had a total of 9 males out of 20. When you use the formula, you always go back to out of your total sample space, plus the number out of 20, plus the number of people that play tennis. So that would be a total of 5 out of 20, minus the probability that a person is male and plays tennis. So the scenario, I'm going to erase these circles that I had from before, the scenario where we have a person that is male and plays tennis is the 2. So right now that 2 is being counted in the number of males and also in the number of people playing tennis, so we want to take that away. So we are left with 9 over 20 plus 5 over 20 minus 2 over 20 is 12 out of 20. That is the same answer I got by just extracting information off of the two-way table. Let's take a look at part 2. Given that the student selected is female, calculate the probability that the student does not play football. So, given that the student is female, calculate the probability that they don't play football. Let's try this again. They don't play football, so I'm going to put F. I'm going to put a little O on there for football. And we are given the probability that they are female, so I'm going to put FE there. And so if you want to just extract your information off of your table, what you can do is reduce your sample space. So I'm going to show this problem 2 ways. One by just extracting data off of the table, the other by using the conditional probability formula. So if I'm given the fact that the student selected is female, I have now limited my sample space down to 11. And then of those 11, how many do not play football? Well, the ones that don't play football would be the ones playing tennis and hockey. So that would be 3 plus 3, which would be 6 out of 11. So that's the fastest way to find a conditional probability off of your table. You reduce your sample space. But I'm going to show that same exact problem using our formula. So for our formula, we are working with, let's get a clean piece of paper here. We are working with a conditional probability. So the probability of A given B is equal to the probability of A and B happening divided by the probability of B happening. So in this particular problem, it's going to be the probability that they don't play football given that they're female. So in the numerator, the probability that they don't play football and also are female divided by the probability of our given condition, which is that they are female. So let's see where this takes us here. So I'm going to do my denominator first, the probability that the person is female. Now, when you use your formula, you always go back to your total sample space. So the probability that they are female would be a total of 11 out of 20. And in the numerator, the probability that they don't play football and are female would be the 3 and the 3. So they are female and they don't play football. So that would be 6, but it's out of the total of 20. And if you clean this up a little bit, that simplifies all the way down to 6 over 11, which is the exact same answer that we got up here for part 2. Just extracting information off of the table, which I encourage you to do because it's faster, and IB accepts that. All right, the last part of the question says 2 students are selected at random. Calculate the probability that neither student plays football. So the probability of the first person not playing football, we would have a total of 20 people. Let's go back to our table. Total of 20 people, and the total number of people that don't play football would be 11. We've got 5 playing tennis and 6 playing hockey. So that would be 11 out of 20. We've got the next student that also doesn't play football. These are 2 separate students. I'm going to separate their probabilities, and so that makes these independent events, which means I can multiply their probabilities together. But here's the deal. If I've already accounted for 1 student, my total sample space has now dropped from 20 down to 19. I only have 19 students left. And of the 11 that don't play football, I've already accounted for 1 of them. So that would leave me with 10 left over. So I now have 11 over 20 times 10 over 19. And we can answer this one here. The 10 goes into 22 times. So we are left with 11 out of 38. Okay, so now you've seen an example of a two-way table with a few variations. Thank you so much for listening. Good luck to you.